Welcome back. We are in the home stretch now. This is to be the last parts of our proof of Hardy Littlewood's theorem for sums of squares. We showed that using the multiplicativity of Gauss sums, that as an exercise, you can get multiplicativity of Kloosterman sums and then rearrange your series as a product of series. Your singular series as a product of p-adic versions. The main point now, sort of the last theorem to end with, will be that each term in this product, in this infinite product, is the volume of a p-adic sphere. How is that the case? Well, we see that we have the following theorem. If I've fixed my prime p and I've fixed the number I want to represent as a sum of squares, then Cp of n, which was this series, is actually equal to a certain limit. And that limit is if I look at a neighborhood, a p-adic neighborhood of the sphere, and I weight it appropriately, then as that neighborhood shrinks, or p-adically, I get a volume of a sphere. This shows that that series is actually clearly non-negative, and will then show that it's positive. How do we do this? Oh, you fix your prime, and we'll actually truncate that series and show that since it's absolutely convergent, we just take the limit of that truncation tending to infinity. Okay, so truncate it, consider the first j plus 1 terms. Right, j starts at 0, so we're going up to j. And the main point here will be that you can complete the exponential sum. Where is that coming from? My Kloosterman sums, each one of them is an average over z mod p to the j in d dimensions, and with another average over the units modulo p to the j. Now for each one of those, I just extend, I consider not just the units mod p to the j, but I consider all the residue classes mod p to the j. And then I take out all the ones that were not coprime to p to the j. That is, they had a factor of p. That's what this is doing right here. That's completing the exponential sum. My sum was incomplete because I just had units, and I've completed it because I actually have now all of z mod p to the j. That's going to be useful because when you have the complete exponential sum, you can use orthogonality usually. Fantastic. And so here's the identity where I've thrown in the extra ones that were missing, the ones that were divisible by p. And now if I sum over j, I get the corresponding identity. Where if j is equal to 0, then the group of units is just adding in the term a equal to 0 and then taking it out. So I'll consider that as an empty sum. All right. Right. Now that we've completed the exponential sum, we just have some simple analysis to do. I take each of these vectors b, and I write it as a factor of p to the j minus 1 times some other vector b prime, plus some remainder term c. So that other vector b prime is now a vector inside of z mod p in d dimensions, and the vector c prime is in z mod p to the j minus 1 in d directions. And what I'm trying to do is I'm trying to handle this last part right here. Wonderful. We just plug it into the exponential sum, and we are going to expand the square again, find some terms that cancel, and get another expression. The way this works is I take a sum over b, and z mod p to the j, d directions of So I'm doing this for my Gauss sum, right? B squared minus n over p to the j minus 1. That is just sum over b again. Oh, sorry, b prime. Z mod p to the d, a sum over c, and z mod p to the j minus 1. And I have e of a, and what's here? I've got p to the j minus 1, b prime plus c squared minus n, all over p to the j minus 1. When we do this, we see that these terms, which have the factor of p to the j minus 1, get washed out by the denominator. And this thing is actually just equal to this, where I've deleted that linear part and I just have the remainder of c. This doesn't depend on b prime anymore, but I have z mod p to the d sums that are all the same. So this is just a factor of p to the d that comes out, right? So that we have just that. Oh, sorry, times p to the d. Right. And you plug this into the above, which means you're going to need a sum over j, right? And yeah, so let's do that now. Sum over j equals 0 to j of kpj of n. That's the sum p to the minus jd. That was the factor from before that I've left out. Oh, I should have had that here too. P to the minus jd. Right, that's this term right here. Great. Of the sum a and z mod p to the j. Sum over b, z mod p to the j to the d. And this expression, ea b squared minus n over q. And then, of course, I'm subtracting the sum over a and z mod p to the j minus 1 and a sum over b as well as this thing, which we just said was actually equal to p, this is actually equal to p to the d and a sum over c and z mod p to the j minus 1 to the d. And that would be, this would be e of a c squared minus n over p to the j minus 1. This sum telescopes. Okay, let me put in the p to the minus jd. That becomes a d minus 1 now. Wait. Sorry. J minus 1. Back. Times d. And the sum telescopes. All I have left is the term at j equals 0. In particular, this is just saying that the sum over, oh, come on. Sum of k p to the j of n from j equals 0 to big J is actually just equal to k, not k, sorry, is equal to p to the minus jd, the sum over a and z mod p to the big J of d, the sum over b and z mod p to the big J. Oh, not a d there. In z mod p to the big J. And this is in d directions, or d dimensions. Again, e of a b squared minus n all over, oops, p to the big J. Now that we've completed our exponential sum, we actually get to apply orthogonality now. Fubinize again to switch the order of summation. And do the sum over a. This equals p to the minus jd, the sum over b and z mod p to the j d. And I pick out whenever this criterion is satisfied. But I do that p to the j times. So this is p to the j times delta naught of b squared minus n. Which of course, I just put this here to get p to the minus j d minus 1. And that sum. Nice. Oh, that's what the orthogonality of characters was doing. The fact that, so what I was just saying was that the sum of e a x over q, a and z mod q, is equal to delta of x, delta naught of x times q, for any q greater than 1, for any q and n. That's what I was just using. Now we see that we have this expression, and it's clearly non-negative. Right, this is always either 0 or 1. And it actually just counts the number of points on the number of points mod p to the j that lie on a z mod p to the j sphere of radius root n. And it normalizes them by what you would expect to be the codimension of that sphere, d minus 1. Sorry, by the dimension of that sphere. So you expect the sphere to have codimension 1, therefore dimension d minus 1. So you weight them with something that has size d minus 1 as an exponent. That's the proof of that. Were there any questions regarding it? Moving forward, we've shown that each term in the singular series is non-negative. Great. We still have to show it's positive for each prime. Again, we got this using the Gauss bound or Weil's inequality as a weaker one, whenever p is sufficiently large. We didn't say what sufficiently large was yet. But let's see why p being small is going to be a problem. In particular, let's take the smallest prime p, the smallest prime, p equal to 2, and see where the difficulty comes in, right? The prime 2 is special in this case because it divides the degree. In fact, it equals the degree. And we have and because of that, when you look at something like a plus b squared, it's just the same as a squared plus b squared mod 2. And whenever you consider higher powers of 2 here, 2 to the k, the cross terms, the 2ab, are always going to pull out some factor, it's going to pull out a factor of 2 here. Okay, that is going to be a problem. So let's see why that's a problem. Let's just calculate some Gauss sums at various rationals for various dyadic rationals. I take G1, 2 of 0, which is just this sum. It's the one-dimensional sum. It has 2 terms in the sum. It's got E of 0 basically, and then E of 1/2, which are 1 and -1 respectively. Therefore, the Gauss sum is 0. And this again is a reflection of our observation from lecture 1 that half of the squares are even and half of the squares are odd, because half of the numbers are even and half the numbers are odd respectively, and squaring preserves even and odd. Okay. Let's consider what happens for 4. If I consider what's happening at 1/4, well, we find that there are 4 terms to consider now. E of 0, E of 1, E of 0 over 4, E of 1 over 4, E of 4 over 4, and then E of 9 over 4, which happens to be 1 over 4 again. And these terms also cancel each other out. But we finally get something now if we go to 8. When we go to 8, we actually get that there's some non-trivial mass here for G180. And that's because we can finally start to see some bias in the squares mod 8. And it turns out to be this value, 4 times e to the pi I over 4. Well, I guess actually my definition of e, it should be minus. We finally see something non-trivial when we get to 8. Okay, the point here is 2 is an odd prime, especially with consideration towards squaring. For higher degrees, you're also going to have to worry about what happens modulo a prime for any prime dividing the degree. So if I have to worry about cubes, and I have to worry about, if I'm looking at sums of cubes, I have to worry about what happens for G of powers of 3, for the Gauss sum at triadic rationals, and for sums of 5th powers at quintic rationals, so on. But we can handle all odd primes using Hensel's lemma pretty quickly. To do this, let's just introduce a little bit of more notation. I'm going to take the sphere, mod p to the j, of radius root n as this. But I'm going to ignore the point 0, the origin, inside z mod p to the j to the d. And now if my prime is odd, meaning greater than 2, the CP factor is bounded from below by this. Which means that we only have to prove that there is a solution for each n, because then this is going to be greater than 0. Okay, so again, the scheme to complete the proof now, we need to show each CP is positive, independent of n. We're going to do that by showing each one of these sets actually contains an element when j is equal to 1. And that gives us our lower bound for 0. But that's only for p greater than 2. We'll have to do something different for 2. Great, so how do we do that? I'm going to fix all I have to do is do this for each element in here. If I take some element x inside Sn of p, which again was just the set of, say, y and z mod p to the d, such that y squared is congruent to n mod p, but excluding 0. By taking a representative in that, all I need to do is show that it lifts to a bunch of representatives modulo p to the j. In fact, this many representatives. Once I do that, I just sum over all the possible x inside Sn of p, and that just counts them. Wonderful. Let's do that. The way we're going to do it, we're going to get this is, okay, without loss of generality, since x is in here and it's non-zero, assume that the first coordinate is non-zero. Then I'm going to take for x2 through xd, I'm going to take all y2 through yd in z mod p to the j such that yi is congruent to xj mod p, or sorry, xi mod p. What the hell's going on here? Apologies. The recent update of Jarboard PDF has made it less usable. So for each of these d-1 remaining coordinates, I just take the obvious lifts up to z mod p to the j from xi being mod p. Right? There are, of course, p to the j minus 1 to the d minus 1 possible xy. Possible y2 through yd. Great. Now that means, what does that mean now? That means we just need to find some lift of x1 that still satisfies our equation, but our equation now takes the form that is mod p to the j instead of mod p. So we had before that n is congruent to the sum of xi squared mod p, which is equivalent to, of course, n minus the sum from I equals 2 to d xi squared equals x1 squared mod p. And because x1 is non-zero, we know that this is not congruent to 0 mod p. We want to lift this to n minus the sum of I equals 2 to d of yi squared congruent to, let's say, y squared. It's this equation we want to solve, mod p to the j, where y can be congruent to 1 mod p. But this is pretty easy. Let's just rewrite this. We fixed y2 through yd. Let's just rewrite this as some a. A is congruent to y squared mod p to the j. And we know that a is congruent to x1 squared mod p. So a much smaller congruence, right? Well, Hansel's lemma tells us that since x1 is non-zero and the derivative of this function, y squared minus a, is just 2y, p is greater than 2, that we can lift, the x is a non-singular solution, and we can lift it mod p to the j for any j. And this gives us our solution y. So it's just Hansel's lemma from here. Are there any questions? Is Hensel's lemma something I should maybe bring up next time, like prepare a little bit on, or no? Everyone happy with that? Sort of the harmonic analysis preliminaries are a bit higher than the number theory ones, but but I am really expecting people to know p-adic numbers, and that would mean Hensel's lemma. But if that's an unreasonable prereq, then I can go back and cover it. Okay, well, if you don't have any opinion on that now, let me know later.
I'm happy with Hensel's lemma, but I can't speak for your intended audience, or indeed for the rest of today's audience.
Fair enough. Well, maybe in the TCC course, I'll use the discussion session to do that. Since Kirsty's happy, I'm happy to move forward. And now so I stated that lemma for odd primes. There's a straightforward way to modify the lemma so that you actually can do it for powers of primes, any power of prime when it's odd, or at least when if your prime is 2, then you have you considering the cube power of 2 or higher when it's at least 8 or 16 and so on. And you have the very obvious modification that you have to weight it by the expected dimension again. I'll leave this proof to the reader. It's really just going to be notationally a little more cumbersome than this. But it again relies on Hensel's lemma and being able to lift things, assuming you have a non-singular solution. And it's getting that non-singularity that is why we assume a higher power of 2. Because when you take the derivative of y squared minus a, I've got 2y there. And that 2 coming from the quadratic power is the nuisance. But it's all very doable. Right. Now let's make effective what are the small primes that I've alluded to in the past lecture. Going back to our Gauss bound, we had this bound for Cp of n minus 1, coming from just using the Gauss bound and summing up a geometric series. In order to show that Cp of n is minus 1 is not 0, it suffices to show that this expression is just less than 1, because then Cp of n has to be close enough to 1 that is not 0. Simple. So let's calculate what small means now. If p is greater than 9, that looks like a q, doesn't it? P is greater than 9, still looks like a q, okay. Then I have p to the 1 minus d over 2 is actually greater than a power of 3, right? So if this is true, and of course, and d, I'm gonna now also use d is greater than or equal to 5. Then I have p to the 1 minus d over 2 is actually less than 3 to the minus 3. Which of course implies that 1 minus p to the 1 minus d over 2 is greater than 26 over 27. And as a result, Cp of n minus 1 is less than or equal to 2 to the d, 27 over 26, p to the 1 minus d over 2. Right? Just plugging that into the above. And now you can calculate that if, so what do I want to do? Right, I want to say that this is less than 1. Okay, want to say that. When is this less than 1? Well, it's going to be less than 1 precisely if p to the d over 2 minus 1 is greater than 2 to the d 27 over 26. I square both sides. And that's the same as p to the d minus 2 greater than 2 to the 2d 27 over 26 squared. Right? And this is, oh yeah, and now I take d over d minus 2 roots. So p is greater than 2 to the 2d 27 over 26 squared to the 1 over d minus 2. Let's clean this up a bit. This is biggest when d is smallest, so d is 5 in this case. And when you just plug this into a calculator, what you end up finding out is that this is roughly 10.20697. In particular, this number is less than 11. And so that means whenever p is at least 11, I have that I am c, so this implies Cp of n is not equal to 0 for p greater than or equal to 11. Right? So my small primes now is actually just the first 4 primes, 2, 3, 5, and 7. I have to show that C2, C3, C5, C3, 7, C7 are all non-zero for each n, whenever d is at least 5. Is that clear that that's what my goal is? And in particular, I have to find non-singular solutions. I can't just plug in 0 for all of the coordinates and get an answer and get that as my solution. But this is actually pretty straightforward, right? Let's see, the first step to doing this, if I have a solution, non-singular solution in d not variables, then I have one in d variables for any d greater than or equal to d naught by just padding with zeros. Okay, so that means I only need to do this for d equals 5, and I'm good. I will actually do this for d equals 4, which is more than I need to do, but it has a fewer number of variables and it's easier to check mentally, right? Okay. Now let's consider p equals 3. If I look at x squared plus y squared mod 3, then I can clearly get values 0 by plugging in, I can clearly get values 1 by taking x equals 0 and y equals 1. I can also get the value 2 by taking 1 and 1. And then, okay, that means I have to worry about 0 left. But for 0, I can get I can't just plug in 0, 0 to get 0. I actually have to consider the equation in 3 variables. And I get a non-singular solution coming from the vector 1, 1, 1. Now in p equals 5, I can similarly get 1 and 2 as before. I can also get 5 now by going 1 squared plus 2 squared, which equals 5. So it gives me 1, 2, and 5. I can also get 4 from going 0 and 2 squared. And that just leaves me with 3 to worry about again. And for that, I can just do 2 squared and 2 squared, which is 8, and that's 3. So I've got 1, 2, 3, 4, 5. Great. I only needed 2 squares for 5. For a 7, again, I just do the sum of 2 squares. I'll get 1 and 2. I'll get 1, 2, 4, and then 5, and that's about it. I have to worry about 3 and 6. And so for 3 and 6, I have to use 3 variables. And you get, for 3, you just take 1, 1, 1 again. That gives 3. And for 6, you just take 1, 1, 2.
You also need to do 0.
Sorry?
You forgot 0.
And for 0, thank you. I did forget 0. For 0, I have to go to 4 variables. Wait, I forgot 0 for 5 as well, didn't I? No,
No, you didn't. You didn't forget 0.
Great. So 0 here is just this is the one that comes from the famous 4 sums of 4 squares thing, and why 3 squares fails. And that I just take 1, 1, 1, 2. That goes to 7, which is, of course, converted to 0 mod 7. Wunderbar. And finally, we deal with the smallest smallest prime, 2. And that actually means I'm going to have to deal with 8, things mod 8. Right, because of this whole non-singularity issue. Again, you can get a bunch of values for sums of 2 squares. And so what are they? X squared plus 2, x squared plus y squared mod 8. Well, I can get 0, 1, or 2 by just plugging in 0 squared or 1 squared or 2 squared into each of these. And also that gives me 5.
Well, hang on a sec. I mean, you can get 0,
right, I
but
can do that with 0 again.
But you can do 2 squared plus 2
and that
squared.
gives me
Yeah.
0.
Yeah. Just sorry, I'm being annoying. I know.
No, I jumped ahead. I had done that in my head, but I didn't say it. Yeah, the 0 here is coming from 2 squared plus 2 squared. Okay. But I'm missing things like, oh no, that also gives me 4. But I'm still missing 7, right? And 6 and 3. The way I get 3 and 6 is the same as before. I get 1, 1, 1 and 1, 1, 2, right? And the way you get 7 is you go up to 4 squares again, where you use 1, 1, 1, 2. And that is all you need to do. Finally, we have completed the proof of Hardy Littlewood's theorem for just squares. Sums are 5 or more squares. Are there any more questions? Oops. Oh, what's going on? Phew. If there are no more questions right now, I will end the recording. Thank you.